Hello everyone, this is Dr. Hopkins with our next video where we're going to do temperature dependence of kinetics. So let's start with a familiar reaction, an exothermic reaction, so the combustion of methane. And we know this is favorable, it gives off energy, it gives off heat, right? This is the burning of natural gas. But the question is, if this is so favorable that it gives off heat, why is it that methane doesn't just, because there's oxygen in the atmosphere all the time, why isn't it that methane doesn't just combust spontaneously? And so, as we were just saying, the products are lower in energy than the reactants. And so why is this stable? It's because we require a spark. We have to light a fire. We have to start the combustion process. And we typically call that the activation energy. And that's related to the kinetics. So delta H, or enthalpy, is related to the thermodynamics. So here's a kind of a general reaction coordinate diagram where we have reactants going to products. It's an exothermic process, so we have energy gained, reactants to products, but you have to overcome some transition state. It has to get into the proper position to react in order to go all the way to products. So this EA is our activation energy. It's a way to rearrange the reactants on the way to products. And then we're explaining the delta E. And so higher temperature makes it easier to overcome that barrier. Hence, it tends to speed up reactions. Okay, so the temperature dependence is reflected in the rate constant. So the concentrations themselves are not going to change with temperature. So the order of the reaction will not change with temperature. So it's all focused into the rate constant. And so we can reflect that, or there's one way to express that. So K is our rate constant. We have this, we have the gas constant. So AE raised to the minus EA, which is our activation energy. R is our gas constant. T is the temperature. And A is some pre-exponential or frequency factor is what we'll call it. And then we can actually linearize that. So if you just took the natural log of both sides, we remove that E, we get the natural log of our rate constant is equal to minus the activation energy over RT, or we could put the activation energy over R times 1 over T plus the natural log of our frequency factor. And so we'll start from this Arrhenius equation, this linear Arrhenius equation. And the way to determine an activation energy, which is the key to the temperature dependence of a reaction, whether a reaction go faster or slower, we can measure a bunch of rate constants versus temperature data. And then if we plot the natural log of K versus 1 over T, the slope contains the activation energy and the y-intercept contains that frequency factor. Now, sometimes you can't really measure too many temperatures. It's very hard to determine the K. It's kind of experimentally unwieldy. So sometimes you just have two temperatures. You can usually assume that frequency factor is constant. And so we can relate a two-temperature measurement where we have the natural log of the ratio of the Ks versus the activation energy over R versus 1 over T. So let's do an example problem just with the two. And so, we started with this idea that, let's get this pencil working. So we got natural log of K over K, so K2 over K1 equals minus EA over R. We're going to solve for EA, 1 over T2 minus 1 over T1. So if we set that up, so that means our activation energy is simply minus, and this would be, now I'm going to substitute in our value. So we're going to make this 2, so 57,600, and that's 2460 times R divided by 1 over, and this is 320 minus 1 over 273. And remember, R is 8.314 joules per Kelvin mole. So we're going to substitute that in. I didn't write it out explicitly. And we can solve. We plug everything into our calculator, and we solve that. We get 48,700 joules per mole, or 48.7 kilojoules per mole. And that's our activation barrier. So in order for this reaction to happen, it needs to find 48,700 joules, or 48.7 kilojoules per mole, in order to overcome that activation barrier, or in order to rearrange into a transition state. And that's how you do those calculations. I'm not going to show how you do the plots. You would just take a bunch of Ks and plot them, and then fit it with use it on Excel, get the equation and the R² equation to know if you've got a line, and then you can extract out all of the data as well. So the takeaways from this lab, so we know that reaction rates are temperature dependent through the rate constant. So our rate law is still the same. The rate constant is the temperature dependent part. Higher temperature typically makes it easier to overcome that activation barrier. And the way to determine the activation barrier is using the Arrhenius equation. So until next time.